Great.
Good evening. First, I would like to thank the organizers of the workshop for providing me an opportunity to present a part of my work as I have carried out as a postdoctoral fellow in the lab of Professor Hadar Steinberg. I'm T.R. Devidas, and I'm going to talk on spectroscopy of barrier defects coupled to superconductors in van der Waals tunnel devices. The schematics shown here is a specific geometry called the NQDS system, where N, QD, and S correspond to a normal metal, a quantum dot, and a superconductor capacitively coupled to each other. In such a system, the different interactions are dictated by the various energy scales present. For example, the charging energy of the quantum dot, which is U, gamma, which is the coupling strength between the dot and the normal or the superconductor electrodes, and delta, the superconducting energy gap. In the regime where the dot couples strongly to the superconductor, we get Andreev bound states within the superconducting energy gap. In a regime where the dot couples more strongly to the normal electrode, spin flip co-tunneling process can lead to formation of condo ground state. And in the regime where the charging energy of the dot is much greater than the coupling strengths, you enter the Coulomb blockade regime where transport is dominated by single electron resonant tunneling processes. Traditionally, NQDS devices were built in systems such as carbon nanotubes and semiconducting quantum dots and nanowires. In our lab, we emulate the NQDS system using van der Waals tunnel devices. And the quantum dot is associated with a defect in the semiconducting barrier, which is used as a tunnel barrier. In most of the work in our lab, the work cause of our lab, the superconductor is the NbSe2, and here too, the S part will be 2H NbSe2. Andreev bound states. So NQDS system in our lab with Andreev bound states was reported by Tondweer, where you could see Andreev bound states in a system. In a recent work, we also observed that you could also enter the condo regime in similar NQDS geometry in van der Waals tunnel devices. The data is under more processing, but you can see that you have a logarithmic temperature dependence of the condo peak, which is a signature of a condo. This talk, I'm going to talk more on the regime where you enter the Coulomb blockade, where what you see here, a Coulomb diamond, is the regular feature in such Coulomb blockade regimes. Since I told you that the quantum dot is a defect, traditionally quantum dots were tuned, had this geometry where you could approach the quantum dot with a gate locally and capacitively tune it. However, our van der Waals tunnel junctions have a very highly planar geometry, which doesn't allow for such approach and capacitive coupling using gate electrode. What we resort to is using graphene. Graphene, with its unique band structure, helps us to tune the dot. How does it happen? Let's take a look at the mechanisms. So assume you have a quantum dot, which is at a distance from a graphene monolayer of graphene. The dot's chemical potential is defined by its own environment. When you let the graphene be, graphene's chemical potential initially be at the Dirac point, as you apply a gate and you charge the graphene, the electrochemical potential penetrates, allows penetration of an electric field, which then shifts the graphene, the quantum dot's chemical potential, and thus we can tune into the quantum dot's energy states. Using such tuning capability of a quantum dot, ACKNOWLEDGEMENT from a lab conducted spectroscopic measurements on monolayer graphene, studying the Landau levels up to fields, very high magnetic fields of 33 Tesla, a feat possible because these defect-based quantum dots are minimally invasive. We now, since the dot has been found to serve as a good spectrometer, we now use them to study tunneling into the superconductor 2H NbSe2. The device geometry is shown here. Monolayer graphene is exfoliated on a silicon with a 285 nanometer silicon oxide. the semiconducting barrier MOS2 is exfoliated, and 2HNBSE2 is exfoliated on top of it. All of it is done via dry stamping techniques. The backgate is applied by using across the oxide, and we tunnel through the from graphene to the superconductor. An optical image of the device is shown here. As you see the differential conductor, as we do the differential conductance measurement, you see that we get a very nice differential conductance spectra of NbAc2, and you see as you apply a backgate, we do see gate affected changes in the spectrum, which we then associate with dot assisted tunneling. So the total differential conductance we define as a sum of a direct tunneling and a dot assisted tunneling. All these measurements were carried out at a temperature of 30 millikelvin in a dilution cryostat. Before going further, let me speak about 2H-NBC2 and why it interests us. 2H-NBC niobium diselenide is a van der Waals superconductor which shows superconductivity even in the monolayer limit. An interesting property of it is the Ising spin-orbit coupling, which is out of plane, such that this property enables it to preserve the superconductivity even at high parallel fields beyond the polyparamagnetic limit. The second thing is it has multiple bands crossing the Fermi surface. You have niobium-derived bands at the K and gamma points, and you also have three-dimensional selenium bands around the gamma point. This has led to debates on what type of superconductivity is in the system, whether it's anisotropic or multiple band system. From our tunneling measurements, if we take this is the first derivative of tunneling current. If you take another derivative, you take the second derivative, we see that you have two features which crop up at 0.6 millivolt and 1.2 millivolt. 1.2 millivolt is the value of the quasi-particle peak, and is the gap, the measured gap of the niobium derived bands, and the one at 0.6 is mostly associated with selenium derived bands. As we proceed with measuring the spectrum over a wide range of gate voltages, and we get a conductance map, VPG versus VSD as a conductance map. As we see, we have a dominant dot assisted tunneling feature on a background of a constant tunneling spectrum. We then subtract an averaged background over different gate scans to just extract the dot assisted tunneling current. If you now look at it at a high resolution one, we see that the dot assisted tunneling current sees the superconductive gap, specifically the second gap. The black dashed lines here actually represent how the spectrum should be if the electrode was not a superconductor. So we now try to understand how the spectrum, what are the different regions in the map. So the region marked 1 corresponds to the region where you have the graphene's the quantum dots energy resonant with both graphene and the Fermi energy of the superconductor. Since there are no states available for tunneling into, you don't have any tunneling current here. As you move to a value of 0.6 millivolt, we see that here the chemical potential of the dot of this specific state is resonant with the second gap of the inner gap of the NbAc2 superconductor. So we have onset of tunneling current. Along this diagonal, which is called the source resonance diagonal, the chemical potential of the dot is in resonant with that of the graphene, and along the diagonal label 4, it is resonant with that of states on the superconductor. So we now so how do you use the quantum dot as a spectrometer? Along this source resonant diagonal, label 3 from the previous figure, what happens is as you move along this source resonance diagonal, the dot scans the complete density of state of the superconductor, and hence it maps exactly the density of the superconductor, density of state of the superconductor. We know this is where the dot's energy should be 0. So we measure along a path which is parallel to the source diagonal resonance, and try to extract the density of states. However, as we measure along this diagonal, we get a feature which is similar to the second derivative which we saw earlier. So the dot assisted tunneling current actually measures directly the second derivative of the tunneling current. How do we understand it? We know that the differential conductance from tunneling phenomena is directly proportional to the density of states of the superconductor if one side is a normal metal. However, in the presence of a quantum dot, which has a Dirac delta Fermi distribution, the presence of it actually helps to measure the derivative of the differential conductance itself. We further try to understand. We try to further understand why you see that. Okay, we see that the direct tunnel rings, direct second derivative of the direct tunneling is, and that of the dot assisted tunneling current have different coupling to the two features. For example, this one couples strongly to to the outer gap, whereas this strongly couples to the inner gap. So we try to analyze the spectrum using the Macmillan model, which is used to analyze NBSE2. We see that which is a two-gap superconducting model. We see that the tunnel selectivity factor n1 by n2, which defines the tunnel selectivity for each electron. We see that in the dot assisted tunneling, dot assisted one, we actually see the tunnel selectivity to be more towards the inner gap. We further also measure the evolution of the dots characteristics with magnetic field. We see that you have a spin splitting of the ground state in parallel magnetic field as you increase the field. Extracting these values, we get a Zeeman energy. From the Zeeman energy, we get the Landigi factor of the dot, which corresponds to 1.7, which means that the dot itself is of an atomic size, which corresponds to say that dot is of an atomic size. But what's interesting is also that the splitting is on one side. So how do we understand that? In the absence of a magnetic field, you have this energy resonant, this level of the dot resonant with the inner superconductor. So you have resonant tunneling. However, in the presence of a magnetic field, you have a Zeeman splitting of the level. If the dot couples weakly to the superconductor, weakly to the normal metal than the superconductor, then you already have a single state occupied, which then Coulomb blockades any other movement of electron. However, if the dot is coupled strongly to the normal metal, then any dot transferred would tunnel into the dot. Any electron tunneling into the dot would immediately tunnel off to the normal metal side. So hence we have an asymmetric coupling which defines a spin splitting on one side. Using this model, we model and we reproduce the data which we measured. So in summary, atomic defects in TMD materials can behave as quantum dots, and these quantum dots can be used as very sensitive spectrometer. And in NBSE2, the quantum dot couples strongly to the second gap that originate from selenium derived bands. The selectivity may be related to an orbital mechanism. Acknowledge the funding agency, and thank you again for the opportunity.
Thank you very much, Devidas, for such a great talk and for being on the schedule. Actually, so we have some time for questions. Please, I have one from Herman. If you want to unmute your microphone.
Yeah, hello. Hi, a very nice talk. So I did not really understand. I mean, so you do not see any Shiva-like states related to your dot, right?
No.
Okay. Did you think of that, or?
I didn't think of it, but definitely I will think of it. But we know this dot is not supposed. We haven't seen any Shiva-like states from the dot right till now. We actually have more spectrum we have more dots which come up. So we did have more devices which gave similar spectra, and all of them reproduced the result I just showed. They help you to get a good spectrum of the superconductor.
Okay, thank you.